Welcome back. So after, can you hear me? Yeah, okay. After a series of talks on the equations of state in general and the thermal evolution, so we move on to a series of talks on the crust of neutron stars and magnetic fields. And so here is our first speaker about the inner crust of neutron stars.
Thank you. Hello, everybody. I'm going to talk about the nucleus-nucleus interactions in the inner crust of neutron stars. This work has been done with Professor Petik from Copenhagen. So let me start by first thanking the organizers for organizing such a nice conference and giving me opportunity to talk. And this first slide is about the schematic structure of neutron star, just to remind you what is the common picture. So this picture shows a slice of the inner structure. Generally, it is accepted that there is a solid crust under ordinary conditions when the star is sufficiently cold, this crystallizes, and there is two parts of the crust. One contains just electrons and nuclei. At the bottom layer of this crust, one finds unbound neutrons, so these are called drip neutrons also. In the core, the composition is not generally known, but what we can say is that it is some sort of uniform nuclear matter. So we will deal in this talk with the crust. And here I try to make a picture how it looks like. So above the neutron drip density, when the density is lower, we have just this Coulomb crystal. Generally, Coulomb crystals are body cubic centered, as you can see here. Then if we increase the density, we get neutronization of matter because the electrons start to hit the nuclei, and we get these neutrons between the nuclei. And this is also this has been obtained already in 1973. Here is a figure from this classical paper by Nigili and Vaterin, where we can see a unit cell of a crystal and proton density and neutron density. So as density increases, we can see that the protons still remain localized, but the neutron density extends further than the size of the nucleus. So the size of a nucleus is determined by the proton density. And all the protons are bound for these moderate densities. But the neutrons are unbound. So this becomes complicated. However, it is important to understand the crust because of observational reasons, first of all. There are a few reasons for that. First, when the neutron star cools, the heat passes from the core through the crust, and so the crust affects the cooling properties. Also, there are situations when there is accretion, and as the matter falls on the crust, then the accretion stops, and the crust cools again. So this can be observed in real time. These sources are called the low mass X-ray binaries. Also, there is a motivation to study the crust because it is believed that there are torsional oscillations after the X-ray bursts. So the reason is simple. This is just because the crust is a rigid body, so it can support torsional oscillations, and those oscillations couple to magnetosphere, so this is a complicated problem. This is very active direction of studies to identify quasi-periodic oscillations and to model them using the internal structure and models of magnetic field inside neutron stars, so this is very complicated. Also, everyone knows there is such a phenomenon as glitches. So when we have some rotation of neutron star, and then we observe sudden spin up of the crust. It is believed to be related to transfer of angular momentum to the outer layers. And so it is important to understand how this angular momentum is transferred. So it is, of course, strongly connected to the structure of the inner crust and its properties. So I think there is enough motivation to go further. And here I just want to tell you in brief about the nature of the collective modes in the inner crust. So when we have both nuclear lattice and the superfluid neutrons, we can write, of course, equations of motion for it. Two obvious equations are continuity equations. Those are different. So the first one is for protons. You can see that the proton density changes due to proton velocity. So when the ion moves, we have some change in the proton density. This is obvious. But for superfluid neutrons, the situation is trickier, because the change of a neutron density can happen because of velocity of superfluid neutrons and because of motion of nuclei. So we have two terms here. So the reason for that is that we can't distinguish actually between the neutrons outside and inside, these identical particles. So we somehow take into account that the neutron currents are given by a linear combination of momentum of neutrons and the velocity of protons. So this is a mixed description. So, but this distinction between velocities and momenta becomes increasingly important in the core. So one can do another talk about that. So let's go further. Here is the standard Josephson equation for the superfluid neutrons. So this theta is the superfluid phase. Gradient of theta gives us the momentum Vn. In the literature, it's usually called the superfluid velocity, but it is actually a momentum. Finally, there is a dynamical equation for momentum of the lattice. And you can see here it includes the pressure contribution, which is isotropic. And this anisotropic part is related to shear properties. This shear modulus S is also an important quantity. So actually, in a real matter, we have a non-ideal crystal. It's a polycrystal. So when we estimate S, we need to take this into account. Ogata and Ishimaru in the 90s did this calculation for the polycrystal, but they used the Voigt average, which gives the upper bound. So actually, this is another subtle issue. Let's go further. Here, I just want to show you what we do with those equations of motion. We can linearize them. So we obtain mode speeds given by this equation. And you can easily see that when this term becomes positive, this reduces, and V plus minus squared is always positive, so the situation is stable. However, when this becomes negative, when this term becomes negative, the expression under the square root wins this one, so V plus minus squared can be negative, which signals instability. So here is the natural condition for stability, is that this quantity is positive. So this shear contribution is actually numerically negligible. So we shall look only at this term and at this term. And so if we want to study modes on wave numbers larger than zero limit, so on a shorter wavelength, then we need to leave the approximation of local electric neutrality. And in this case, we can write a generalized equation for the phases. Here I show an example from the uniform nuclear matter when we have superfluid protons as well. And we have nuclear parts in the chemical potentials and also a contribution due to the electric field. So we can express everything, and eventually we can get an expression for perturbation of this general chemical potential, which shows us that we have in the compressibility for protons a contribution from nuclear forces and contribution from interaction of nuclei with the electrons. So in other words, this is just the electron compressibility. For the long wavelengths, we should take a certain form of the response function. This is the dielectric function. So as a next step, we just take a static approximation for the response function of the electrons, and we get this expression for the compressibility of protons, which includes the nuclear compressibility. This is due to lattice and some other forces, which we will study later. And here is the piece due to the electrons. So this is a figure from our previous work done in 2014. So in this work, we considered perturbations of protons on the short wavelengths. So then we needed to remove the electron contribution. And using this formula, we tried to do that. But we also assumed that there is isotropy of EPP, and we obtained instability with the maximum growth rate at the brilliant zone boundary, and we obtained this phase transition for the crystal structure. But then we wanted to check this analytically, and we adopted a simple model where we neglected Coulomb forces. So we considered just a two-component matter. Here is the void. This is just a void without Coulomb contributions because the forces are short range. So in this two-component system, we have induced and direct interactions. The situation is similar to interaction of helium-4 and helium-3 mixtures. For the second order of energy perturbation, we can write an expansion, and then we see that we have a direct piece and an induced piece. So then we straightforwardly calculated what is the direct interaction. We found this expression by simply assuming that we create voids V2, which are like nuclei, and then they interact between each other with the help of the neutrons outside. So for the direct interaction, we obtain this quantity, and then for the induced interaction, I can go into details if you wish after the talk. We obtain the same quantity. So in conclusion, we obtain that if we neglect long-range force, we just get 0 for this. And then we wanted to find out the reason for discrepancy. So we considered contribution due to two-phonon exchange. And here we just removed the lattice and the electron parts. We found that there is still instability. The reason is probably that it is tricky to remove Coulomb contributions to ENN and ENP. So then we considered long-range part of the interaction, which is the two-phonon exchange. So we made evaluation of this first diagram just to find out the order of magnitude of the effect. So in order to do this, we just introduced the second quantization, estimated the vertex, found the R to the -7 dependence, which is the Casimir interaction. And then we estimated its magnitude. It turns out it's many orders of magnitude smaller than the Coulomb interaction. So this figure shows that for the coupled modes, it's very important for the coupled mode, the measure of mixing is very much dependent on the superfluid density of neutrons. Here is a figure with the collective modes calculated with the superfluid density equal to density outside of neutrons. And here little dots show the results when we take the superfluid density from the Nicolas Chamel's work. So this shows the strong dependence. And then we have the measure of mixing also very strongly dependent. Here we can see about 30 compared to Chamel's results or to results without this picture of Chamel with the Bragg scattering. But it is a challenge to understand the conduction neutrons. So the reasons are listed here. And then I just briefly show you some recent results. Here is the Chamel's work, where he obtains that effective mass of neutron can be more than 10 times bigger than the mass of a bare neutron. However, the pairing has not been included. In other work, for a limiting case, when the Cooper pair size is much smaller than the cell size, Martin and Urban obtained that we actually don't get such a reduction in the superfluid density. So this is very important. And also there is a very recent work by Petik and Watanabe who showed that using the Boголюбов-de Gennes approach, we can deal with the case when the Cooper pair size is of the order of cell size. So they did not get the same reduction of superfluid density as Nicolas Chamel has done. So this is also very important, just notice about that. Here are just the take-home messages that actually robust arguments exist that the crystal structure is BCC. The Casimir interaction is very weak between the nuclei. So the Landau damping is very sensitive to the superfluid neutron density. I can comment on this in the question section. And the conduction neutrons are very important observationally. So here are conclusions, and thank you for attention.
Thank you very much. Any questions? So, well, if not, let's thank our speaker again, and we switch to our next speaker.